This is MEI Statistics Minor, Discrete Random Variables for the Geometric Distribution. 4.3 Mean and Variance. So, if x is distributed geometrically with probability of success p, then we recall that the probability that x equals x is given by this formula. P times 1 minus p to the x minus 1 for positive integers, 0 otherwise. So, we can calculate the expected value of x. We know that to be equal to the sum from x equals 1 up to infinity of x times the probability that x equals x. Going from 1 up to infinity ensures that we consider all positive integers. So, subbing in the formula above, that is xp times 1 minus p to the x minus 1. If I then rewrite this in terms of q, that's the sum from x equals 1 up to infinity of x, p is equal to 1 minus q, 1 minus p is equal to q. So we now see that rather than having a large bracket to this big power, we've only got a single value to this power. And now we can very quickly multiply this bracket out to get x times q to the x minus 1 minus x times q to the x, because q times q to the x minus 1 is q to the x. We can then split apart this sum so that we are subtracting this other sum. So what I need to do now is, for this first sum, I'm going to shift the index being this x here. And I'm going to shift it downwards so that it's now going to start from 0 up to infinity. However, since I'm doing that, I need to make sure that I'm adding on 1 to each of these. So I'm going to get an x plus 1 and a q to the power of x minus 1 plus 1, which is a q to the x. Have a go at it yourselves with some actual numbers if you don't believe that's the case, but hopefully you'll see that it is. And I'm also going to do a similar thing here, although I'm not going to shift anything, but I'm simply going to start it at 0, because I know that when x is 0, this term is actually 0, so they are one and the same. But it's important that I get those two limits exactly the same. Again, have a look through that and check you're happy with it. Once I have those, I've got two of the same limits, so I can now combine those back together. So I have the sum from x equals 0 up to infinity of x plus 1 q to the x minus x q to the x. Multiply out that bracket. I'm going to have x q to the x plus q to the x minus x q to the x. And you can see why that's beneficial to us, because that is going to cancel out with that. We're going to simply end up with x equals 0 up to infinity of q to the x. That is, of course, a geometric series and a sum to infinity, which is equal to the first term. Well, when x is equal to 0, that's going to be 1 divided by 1 minus the common ratio, which in this case is q. 1 minus q is equal to p, so that is 1 over p. You're not required to know that proof, but I think it's quite an interesting thing to see. The variance proof is of a similar form. So, if x is distributed geometrically with probability of success p, the expected value of x is 1 over p, and the variance of x is 1 minus p all over p squared. Both are in the formula book, and you can use those freely. So in my first example, probability that a pool player pots a ball on the initial break of a game is 0.4, so that is equal to P. Find the expected number of games and the corresponding variance and standard deviation before this player first pots a ball on the initial break. So as always, we want to define our random variable. So let x equal the number of games before the player pots a ball on the break. X is distributed geometrically with probability of success 0.4. So our expected value of x is 1 over p, that's 1 over 0.4, which is 2.5. So we would expect to pot off the break every 2.5 games on average. Similarly, the variance of x is 1 minus p over p squared, so that is 0.6 over 0.4 squared, which is 3.75. And correspondingly, our standard deviation is the square root of the variance, which is 1.94 to 3 significant figures. And that's the final video on discrete random variables for the geometric distribution.